Good afternoon, everyone. Today I will present my credit card approval classifier and explain how I apply the responsible AI principles in the modeling process. The goal of this project was not only to build a model that predicts whether a credit card application should be approved, but also to make sure the model is fair, explainable, and suitable for a real banking environment. In financial services, model performance matters, but so do transparency, governancy, and the potential impact of decisions on customers. I began with exploratory data analysis and data preparation. First, I checked the structure of the dataset, review missing values, examined the target distribution and separated the variables into numerical and categorical features. This was important because different types of variables require different pre-processing steps. I used a pipeline approach so that numerical variables could be imputed and, and scaled, while categorical variables could be imputed and one-hot encoded. I also removed ID types columns because they do not provide meaningful predictive value. Next, I selected evaluation metrics that are appropriate for credit approval. I did not rely only on accuracy because in lending, different prediction errors create different business consequences. If the model incorrectly approves a risky application, the bank may face higher default risk. If it incorrectly rejects a qualified application, the bank may lose revenue and damage customer experiences. For that reason, I evaluated the model using accuracy, precision, recall, F1 score, and ROC AUC. Precision helps assess the quality of approvals. Recall shows how well the model identifies eligible applicants. F1 score balances the two, and ROC AUC measures how well the model separates stronger applicants from weaker ones across different thresholds. For model selection, I compared multiple classifiers rather than assuming one model would be best. I tested logistic regression, random forest, and the light GBM using cross-validation. This comparison was important because the best model is not simply the most complex one, but the one that provides the strongest balance between predictive performance and stability. I select the final model based mainly on cross-validation, ROC, AUC, and the F1 score, because these metrics were the most relevant to the business problem. After selecting a final model, I evaluated it on the test set and reviewed the confusion metrics to better understand the types of errors being made. I also used a learning curve to assess whether the model was overfitting, underfitting, or generalizing uh, reasonably well. This is important because a model that performs well only on training data may not be reliable in real-world deployment. The learning curve helps show whether performance remained stable as the amount of training data increases. A major part of this project was responsible AI. Because credit approval is a high impact decision, predict predictive performance alone is not enough. The model should also be assessed for fairness and transparency. To address To adjust fairness, I first removed direct sensitive variables such as gender or sex from the training when uh, from the training when available. However, I also recognize that removing a sensitive feature does not guarantee fairness because other variables may still act as proxies. For that reason, I conduct fairness evaluation after training by comparing model behavior across groups. I used fairness metrics such as demographic party difference and the equalized odds difference along with group level performance summarize where possible. These checks help show whether approval rates or error patterns differ significantly across applicants groups. I also included explainability methods. In a banking context, it is important to understand not just whether a mode works, but why it makes certain predictions. For global explainability, I use methods such as uh, permaturation importance and the SHAP summary analysis to identify the main factors driving model behavior across the four applicants' population. For local explainability, I use SHAP or LIME to explain the prediction for individual applicants. This is useful because it supports int internal review, mode governance, and more transparent communication around the decisions. From a business perspective, this model could improve efficiency and the consistency in credit decision making. At the same time, the responsible AI elements help reduce risk by uh, improving fairness review, transparency, and governance readiness. In practice, a model like this should not be treated as fully autonomous. It should be deployed with monitoring, regular fairness checks, and human oversight for higher risk cases. In conclusion, this project shows that a good credit approval model should not be judged only by predictive accuracy. In a real financial institution, the model must also be fair, explainable, and reliable. My final workflow combined uh, my my final workflow combined data preparation, multi-metric evaluation, model comparison, learning curves analysis, fairness assessment, and explainable techniques to create a more responsible machine learning solution for credit approval.